So welcome to Silicon guys. So now in this lecture we will talk about the MOS IV characteristics and we will discuss what threshold voltage is with respect to MOSFET. So first we need to understand what an IV characteristic is. So I here is the current and the V is the voltage. So we want to understand MOSFET current and voltage dependencies and how they are related to each other. So that is the first thing we will discuss here. And the problem is like why IV, right? Why current and voltages we need to discuss. So basically there is a thing called abstraction, right? Since MOSFET is a device, right? So MOSFET is a device. So this is the device that last time I have drawn the circuit like this, and this is a let's say N plus region, and here is the P substrate, right? So this is the P substrate, and this is the gate, right? And this is the oxide. So the thing is, why we want to study characteristics of the MOSFET. The reason is simple, because every time we don't want to analyze the circuit from the device physics level, right? So the thing is, we want to understand it. It is like a black box, right? We will see that this is a symbol, right? It's a black box, and we will understand like how its gate and it is controlling the operation, right? And here it is, for example, the drain and the source, and what will be the output here and what will be the input here, right? So input will be given here, output will be collected from here, and in between what's happening, we don't want to analyze it every time, right? This particular device physics we don't want to analyze. So to understand that, we want to understand the device characteristics, right? So for this particular characterization, we want to have an understanding, clear understanding of how I, that is a current, and the voltage, like it will have some kind of dependency, right? So we want to understand like in the upcoming lectures like what this graphs look like, right? So that is the thing. So motivation is simple, because for example there is a op-amp circuit, so it contains a lot of transistors. It contains around, let's say, 20 plus transistors. So to understand the whole op-amp circuit, we can't analyze 20 transistor one by one from the device physics point of view. So we want to understand the characteristics of the MOS. So that will be the advantage of this abstraction. Okay, so coming to the next part. So now here we will discuss about the MOSFET operation. So in this, you will see that in this diagram, we are applying the positive voltage here. So we are positive gate voltage applied here, right? Positive gate voltage we are applying here. What that do is, it will be a simple, from the charge perspective, if we see, we know that this is a P substrate, right? P substrate. And here you can see that if positive voltage is given here, right? And what it will do is, it will simply repel the positive charges from here to here. Like it will penetrate towards the P substrate, right? It will come down actually, right? So that will happen. So So let's assume if we are applying the gate voltage 0, nothing will happen and it will be just null and void. Everything will be 0, 0 currents, 0 thing, right? But once we start increasing the voltages, right? So let's say the positive voltage. So this will happen that positive ions will come down a bit, and it will because of the repulsion of the charge carriers, right? So what will happen is positive charges will be come here, right? In the previous slide, if you see, the positive charges will come here. So what will remain is only the negative charges, right? Because we know that positive and negative charges, when they stay together, they are electrically neutral now. But what will happen is they are they are the negative charges. Why? Because the positive charges went here, right? Positive charges went here. All the positive charges are inside the deep inside the P substrate region, and these negative ions are basically Negative ions are basically immobile. Immobile means simple that they won't help in the, they don't participate in the conduction of the electricity, right? So that is the thing. But what we will notice that here there is a channel formation here. If you see, if you see, this is a channel formation here, right? This is a channel formed, right? And so the thing is, we call it a depletion layer. Okay, so we call it a depletion layer. So depletion region will be formed here. Simple, right? It's a basic understanding from the charge perspective, right? And the next thing that we need to analyze is, only we have applied here the positive gate voltage, but there is no carrier since all the negative ions are immobile. So ideally what we can analyze is, we can say that no current. So basically here the current here, that is I for example, will be zero. Why? Because no free charge are there, no free charges are there. So that is the reason of the zero currents. So so there is another perspective. For example, the if you just imagine this diagram like this, the basic MOSFET, why I'm drawing again and again, just to make you a sense that how this structure, and to keep you in the habit to draw this structure from the understanding point of view. I'm very bad with the drawing part, but yeah, thanks for bearing with me. Let me try to draw it here. So this is the oxide part, and this is the diffusion part, and this is my substrate, P substrate, and this is the gate, this is the source, this is the drain, right? So here if you see, we are applying voltage at this region, right? This particular region, this region we are applying the voltage. And here also everything is like a, a metal plate, and in between this SiO2, that is silicon dioxide. So this is a dielectric kind of thing. So what's happening is, so this particular capacitance, so this particular capacitance is because of this region, right? And one more thing is, and this particular capacitance is getting formed because of the, this depletion, right? This depletion, whatever is getting formed here. Earlier in the previous slide, we have understand that this depletion region is getting formed. So with the depletion region, with respect to the metal, this particular, right? So this is a depletion region, for example. So this is getting equivalent capacitance formation. So from this circuit, can you analyze like what this circuit is? It's very simple circuit. For example, I will try to simplify it further. It's just a voltage divider, right? It's like this. If you know, this is Cox and this is C depletion region. So here, if you see, if you just find the voltage here, so it's nothing, it's just a voltage getting divided here. Whatever voltage we are applying at Vg, so that is getting divided here, right? So that is the thing. So the next part we will discuss is the formation of the inversion layer, right? So in the previous slide, what we discuss is the formation of the depletion region, right? So there is a good a quantification that we need to do now here itself, that when Vg increases, this width of depletion, right? Whatever this yellow drawn layer, the more positive charge we apply at the gate, more the width, right, of the depletion region. That is a base concept. Coming to the next slide. So we are using the word inversion here. So the question might arise, why inversion word is getting used here. So just assume if we keep on increasing the positive voltage here, so positive voltage will be accumulated here, and what it will do is it will, you know, push down, repel down all the charges, right, in the diffusion towards the, sorry, not diffusion, the substrate, the p substrate, and leave behind the immobile, this negative ions. But if we further increase it, right, if we increase it further, what will happen is electron from this particular region, they started flowing to this channel formation, right, and they will contribute it in the channel formation. Why negative, sorry, electron will come here? Because of this positive biases, because positive will attract the negative. So once we increase the Vg further, what it will do is it will start attracting the negative charges, that is the electrons. This dash is nothing but just a electron representation. So these all are the electrons. So basically my channel, earlier they were negative ions, now they are electrons. So the thing is my channel starts getting inverted, right? We can say that inversion, right? Because I'll tell you the reason exact why it is called inversion. Because earlier we have this structure like this, and we have this p substrate. So p substrate mean the positive substrate, right? And here we have started accumulating the negative charges. Those are the electrons, right? Those are electrons. So basically earlier, what was the material here? It's the p type. Now the material here is the electron. So basically the channel got inverted. So we are telling it as an inversion layer, right? So inversion. So inversion layer is getting formed here. Why? Because this earlier p substrate, p type material was there. Now the it is replaced by the inversion layer of the electrons. So that's why it is called the inversion layer. So that is the thing. And the good question should be arised here, like how and why this electron, like what are the contributors of this electrons? So majorly the contribution is coming from this, basically the n plus region, right? N plus region is heavily loaded with the electrons. So those electrons will get accumulate here once we have sufficiently large voltage applied, right? So now there is a good concept called the threshold voltage. So this is an important concept called threshold voltage, right? We called it VTH, right? In the books, we called it VTH. We call it VTH, and and the concept of VTH is simple, that VTH is that particular gate voltage we apply when when the concentration of electrons at this region become equivalent to the the p type concentration. So basically once the p type concentration fully inverted by the electron concentration here, so at that particular gate voltage we call it a threshold voltage. So so hope I'm clear that what's the threshold voltage is. So there is a famous equation of the threshold voltage which says that phi ms plus 2 phi f plus q of depletion, right, and c ox. So here phi f is nothing, it's a simple, you know, phi f is equal to kt divided by q ln n substrate, that is n concentration, substrate concentration divided by intrinsic concentration. right? And K here is the Boltzmann's constant, and Q is the electron charge, and N sub is the doping density of the substrate, and Ni is generally we call it as a density of the electrons in the undoped silicon. And this Q DEP is nothing, it's just a charge in the depletion region. And Cox, from the name itself, we can conclude that it's a gate oxide capacitance per unit area. Now, there is one more relation of this Q depletion. So, in the subject of EDC, we must have heard this formula. I just write this formula just for the, so this 4Q epsilon of silicon phi F multiplied by the N substrate concentration under root. So, from here, we can simply uh, say that in practice, the native threshold voltage value obtained from the above equation, right, may not be suited to circuit design, right? For example, what I mean to say is, let's say if VTH is 0 and the device does not turn off for VG greater than 0. So for this reason, the threshold voltage is typically adjusted by the implantation of the dopant, right, into the channel area during the device fabrication. So basically, in essence, in essence, altering the doping level of the substrate near the oxide interface. So that is the whole purpose. So hope I am clear with this definition of the threshold voltage. Coming to the next slide. So formation of the inversion layer in the PFET. So in the previous slides, we have only discussed about the NFET regions, right? Oh, sorry, the NFET MOSFET, NMOS. Now we are going to discuss about the PMOS. So here, this makes it a PMOS, and here we have an N substrate. We call it a N well, right? So simple concept, the same concept, but the thing is, everything will remain same. So the turn on phenomena in a MOS device, basically in the PMOS device, is similar to that of the NFET device, but with all the polarities reversed. So basically, if you focus on this figure, you will notice that if gate to source voltage becomes sufficiently negative, right? This gate to source voltage, source we are applying 0, that is ground, and this gate we are applying the negative voltage. So if the gate source voltage is sufficiently negative, an inversion layer consisting of the holes is getting formed at the oxide silicon interface. Hope I'm clear to explain that basically inversion will happen. Why inversion? We call it the same concept as the previous. Here we have n-type substrate. Now this positive charges will be accumulated here. So basically my n-type earlier was replaced by the positive charges here. So what it do is, it is called the inversion. Just previously we discussed for the NMOS, right? So this plus charges are nothing but just the holes is formed at the oxide silicon interface. So it's providing a conduction path between the source and drain, right? So basically it is going to conduct from here to here, right? So it's going to give me a conduction path, right? So that is a threshold voltage of a PMOS device, right? Where this inversion will happen. And that's why for the PMOS devices, we know this fact that VTH are generally negative. Negative because this gate voltage we negatively applied, so that's why we call it as a negative. And that's why in numericals we will always take this VTH modulus, right? So that is the whole reason of this VTH.